Hello everyone. So in this video, let's talk about the lowest common ancestor problem in a binary tree. It's a very standard problem and it leads down to a very lot of variations and different type of problems. So let's talk about this problem. I'll tell you to solve this in a very simplest and very easy manner. So let's talk about the problem statement first. You are given a binary tree as you can see here. Binary tree is that for every node there can be at most two child. Okay, you have to find out the lowest common ancestor of two given nodes in the tree. So you are given two nodes. Okay, for the nodes you are given two values. Okay, let's assume as you can see in this tree, you are given 5 and q equal to 1. So for these two nodes, what is the lowest common ancestor? Let's talk about what lowest common ancestor means. So what you can see is that if you have these two nodes, the ancestor is the node that is the parent of both of these. The node that is the first common between these two nodes if you go from this node towards the root node. Okay, that you can understand. So let's assume that this is one more type of. If I want to find out the ancestor of this and this, ancestor means the common node between the path if you go from this node to the top and from this node to the top. So as you can see, if you go to this node and if you go to this node is common between the path from going from this node to the top. Same goes for here. So that is what an ancestor is, and you have to find out the lowest common ancestor. So lowest you can see that first common ancestor. So let's understand that as well. Let's say I want to find out the ancestor for this and this. Now, as you can see, this leads down to this, and both leads down to this. So this is the first common ancestor. This can also be an ancestor. So every node that is now above this are all ancestors, but I want to find out the lowest. Okay, the lowest common ancestor is this node. Now, how can you find it out? So ancestor means that this node is common between this path and this path to go from this node to the top. So which means that for every node, I can just check that if this is the common ancestor, then one node. So I'm looking for two nodes. Okay, I'm looking for P and Q. So this is a common ancestor if and only if one side has to be a value P and the other side has to be value, or vice versa. Others like this side can be Q. So this subtree, if somehow this subtree has one value and this subtree has another value, which means that this is the common ancestor. That is the very simple approach or very simple observation that you can make, that this node has to be common ancestor if the left subtree has one value and the right subtree has one value. Then this is the common between both of these nodes. But let's assume if both of the values are on the left hand side only. As you can see in this example, both of the values I'm looking are on the left hand side. So I will check that whether this is the ancestor. For this to be ancestor, one value has to go on the right hand side, right subtree, and one value has to go on the left subtree. But as you can see, both of them are on the left subtree with respect to this node, which means that this cannot be the lowest common because both of them lies on the left hand side. Then I have to go to the left hand side. So I'll now check this whether this is the common ancestor. For this to be common ancestor, one value has to be on the left subtree, one value has to be on the right subtree, and as you can see here, fine. So this has to be the common ancestor. I hope you understand what I'm trying to say here. There can be also one edge case here that, let's say I'm looking for the common ancestor for P and Q such that this is P and this is Q. Okay. In this scenario, I'll first check that whether this is a common ancestor. No, because both of them are on the left sub. So I will then go to this node. This is the common ancestor. As you can see here, one node is there itself. Like this is already one node, and one is on the right hand side. So this is also common ancestor. because as you can see, like there's no on the left hand side, okay, but this is actually a node, so this is the common between this and this node, so that is why this is also common. So I hope you understand that is the common logic around here. Just check for every node. If both of them lies on the left and right hand side, then it is fine, or else go towards that direction which has both the nodes. Okay, so let's talk about the code part now for this particular. So this is here. What we have done is that this is just like a recursive function because we are doing TFS traversal over this. So what you can see here is that for any traversal, like recursive traversal over tree, we have to have our base conditions and the recursion conditions. Let's talk about the recursion conditions. As you can see, for every node, we'll find out whether the node exists on the left hand side and the right hand side. So I'll write on the function, this common ancestor function will check on the left hand side whether, and I will, because we have P and Q and the values are unique. So all of the node values are unique. So I'll just check that whether P or Q lies on the left side as well in the right side. So this scan will tell me whether there is a node equal to the value P or equal to the value Q on the left side or the right side. So left scan is like left subtree and right. Okay, this will tell us that whether there exists a node equal to P or Q on the left and right. As you can see, if both of the values are not equal, that left scan is also having some pointer value which is like not null, and right is also having a pointer that is not null, which means that both of them has value. Not null, which means that there is some value. If both of them are not null, then it means that whatever route I am on is the actual lowest common ancestor, so I'll return the route. Or else, if that is not the case, which means that only the left hand side, if only the left hand side has the value, then you can say if the left hand side has the value, then as you can obviously that the left hand side has the value, so the ancestor will be in the left hand side. So we'll just print out the left scan or else for the right scan, which is the edge case I've told you. Okay, if only the left hand side has the value, then the left scan or the right scan. And the edge condition is that I will keep on going it until I'll meet a null pointer, which means that I don't have any more nodes to travel to. So in that case, pointer, or else if the route or the node I am on is equal to P or Q, because whatever the node I'm looking for, then I'll return the route, which means that this is what I'm looking for. This is the route I'm looking for. The base condition is that I will keep on traversing. Also show you with the diagram. I will keep on going on the left and right side recursively. This, and whenever I find out the node that is equal to P or Q, I'll return that particular node that yes, we have got the node that true. And this node pointer or node value actually I'll return. So this will return one that okay, I got it. This will also return that okay, I got it. If both of them are not null, then which means that both side we have the value, return the root. If this is not returning one thing, if this is returning, obviously if right is returning, then obviously we have in the right hand side, so return the right, or else left side, so left, and else as you can see, whatever node value we have, if we have reached the root that has the actual value, return the root, or else not, because you have to actually return the pointer. That's the complete logic and the code part for this particular problem. This is a complete, if you talk about the time complexity of this particular problem, as you can see, I'm just traversing over the whole tree once. It is O of number of nodes or number of, as you can see, vertices. Okay, for the whole tree. O of n, you can over time complexity. If you have still more doubts, you can comment down in the comment box of the video. I will see you in the next one. Coding.